Hi, in this video we are going to learn what do we mean by linear versus non-linear reservoir. Okay, and we need this information because we will be using this term when we learn different hydrograph routing methods. So to explain this, what I'm going to do is I'm going to draw a simple reservoir and a pipe outlet. Okay. So let's say this is our water level in the reservoir and this is the height of the water. So we have depth, it has unit of length, and then we have our Q is the discharge. So this will be L cube over T, and let's say the area of our pipe is AP. So AP will be the cross-sectional area of pipe. So this will be L square, and then let's say AR is the area of the reservoir. So if I think of this as a rectangular reservoir, so this is our area from top view. So area will be the reservoir area. So this will be L square, and then S will be the storage, reservoir storage. So this will be L cube, and then S is equal to H times AR, or we can say H is equal to S over AR. Okay, so this is what we have, and then we can write an expression for the discharge, which will be the area of the pipe times the velocity of flow. So we can also say V is the flow velocity from pipe. And this will be L over T. So L over T, these are all dimensions. And then from hydraulics, we know that the expression for V is square root of 2GH. And if you want to know how this is derived, you can go back to your hydraulics note, or hopefully you can find that information in some textbook or online. This is done by simply applying the Bernoulli's equation at the outlet and the reservoir surface. Okay, and then we can say that Q square is equal to AP square times 2GH, or we can say AP square times 2G times S over AR. Okay, and then I can say AP square over AR times 2G times S, and then you can say that this is sort of constant because the area of the pipe is not changing, the area of the reservoir is not changing. G is our gravitational acceleration, so again G is gravitational acceleration. Okay, so this will be L over T square, and then I can bring that constant on the other side. So what I have is S is equal to AR over AP square divided by 1 over 2G times Q square. And if we say that this is a constant, so what I have here is S is equal to KQ square, and K is our constant. Okay, so what I have here is a non-linear reservoir because the storage and discharge has a non-linear relationship because of these two. Or I can generalize this by saying that S is equal to K Q to the power of N. So when N is not equal to 1, we have non-linear reservoir, and when N is equal to 1, we have linear reservoir. Okay, or I can say that S is equal to KQ to the power of N is non-linear, and then S is equal to KQ is linear reservoir. And if I plot this relationship, they may look something like this. So this will be linear, and then this will be non-linear. So S is equal to KQ to the power of N. S is equal to KQ. Okay, so again, I want you to remember these two. When you have a non-linear relationship between the storage and Q, you call it a non-linear reservoir. When the relationship between storage and Q is linear, we have linear reservoir, and we will be using these terms when we apply different routing methods in the next videos. And this is it for this video. Again, I got S is equal to KQ square by assuming a pipe as the outlet. If you use a different type of outlet, instead of KQ square, you may get KQ to the power of something else, but again, it will be a non-linear relationship. Okay, so just remember S is equal to K times Q is linear reservoir. S is equal to K Q to the power of something is non-linear reservoir, and we will learn more about K in the next video. So this is it for this video, and I will see you next time. Thank you very much.